The purpose of this video is to talk about simple pendulums and physical pendulums as they oscillate, and eventually we're going to get to the small angle approximation. Give me just a second, we'll get into it. All right. Let me start by just showing you some examples in the real world. Here is a simple pendulum. We're assuming that the ball has much more mass than the string. And as a result, when this thing oscillates back and forth like this, we're assuming the center of mass is right here at the end of the string. Okay, so you can think of a simple pendulum as ball at the end of a string or point mass at the end of a string. Now you can see here I've written something, the point mass moment of inertia. If you think of this top point as a pivot, right, wherever I'm holding the string here, whoops, as this oscillates, if I could get this to go on the plane there. So my thumb essentially is the pivot point. L, script L here, is the length from the pivot point to the point mass. And the moment of inertia of a point mass is mass times distance squared from the pivot point. So this is going to come in handy because we can do both of these derivations in one step with torque. A lot of times people will do this derivation with forces, and you can do that. Maybe if I have time, I'll do that in a separate video. But I'm going to do the physical pendulum and the simple pendulum at the same time. Here's an example of a physical pendulum. I just put a skateboard bearing here and a meter stick. This actually works well. You can see it's just oscillating back and forth there. And so in this case, this is the center of mass is not all the way at the end. It's somewhere here. And you could make this out of different materials. Like you could, I could tape this onto the end. And so as a result, the center of mass might not always be in the exact center. It might be shifted if you use a heavy weight at the bottom of the pendulum, like you might see in some clocks. So, but the point being is there's going to be some center of mass position. In the homework problems, you'll dig into where exactly that is. For now, let's just assume this center of mass position is some distance we'll call that R center of mass, meaning the radius from the pivot to the location of the center of mass. Obviously, with the meter stick, you'd expect it to be exactly halfway in between. Again, in some other problems, this might be a little different. By doing this derivation this way, this should work for all physical pendulums. All right. So at this point, let's try and analyze this by looking at the sum of torques acting on this. And before I do that, I'm going to get my coordinate system up here. We'll call this X, Y, and so then X goes to Y, goes to out of the page is K hat. Oops, I'll call that Z. And now, if you recall the direction of torques, we can think about this. For example, gravity is causing this thing to twist in this direction, right? And notice I'm using my right hand. So if I put my thumb on the axis along the pivot, I see that this is rotating negative K hat. This is going to be rotating negative K hat. It's going to swing that way. And so you could argue a torque that's causing something to go up would be a positive K hat torque. This would be a negative K hat torque. All right. And here's a subtle point. It's also confusing and frustrating at first. If you remember when we did the oscillations problems, we blindly assumed that the acceleration was in the positive direction and we got a negative number for it. Well, what I'm going to do now is I'm going to blindly assume angular acceleration is in the positive direction, but we could get positive or negative values for it. So you might be saying, dude, I know this thing's going to have a negative angular acceleration. Why don't you just put it the other way? Trust me. Okay, that's what I'm asking you to do here. All right, so let's go ahead and write down the sum of torques is equal to I alpha. And here I'm going to say in the K hat. Again, K hat meaning out of the page torque, meaning line up your thumb with the axis, the thumb of your right hand with the axis, and we're calling this the positive direction. Okay, counterclockwise normal math direction. Well, let's think about it. What is the force that's going to cause this thing to angularly accelerate? If we have a pivot with negligible friction, right? We used a skateboard bearing, so we don't have a lot of friction up here, right? There is a force at the pivot holding it up, but that's not what we have to worry about. That doesn't cause a torque. The line of action for the reaction force, right? So you might be saying, oh, well, the pivot has to hold this thing up. Maybe there's a force here, Ry or Rx. In this case, those cause no torque because the line of action for those forces runs through the pivot. We do have a torque right here. There's a force mg downwards. We could figure out the torque for this, and if you recall, the equation for torque is R cross F, or you could use RF sine theta and then plug in the direction from a right-hand rule. I'm going to say that again. R cross F gives you torque, the vector, pseudo-vector, whatever. But we could get the magnitude by getting RF sine theta. What does R mean here? That's the distance from the pivot to point where force applied. Oh my gosh, that's a long. I'm going to say that again. In this torque equation, R is, here it's not a vector. Note right here, you'd have to use the vector displacement from the pivot to the force. Here we're going the distance from the pivot to the point where the force is applied. From the pivot to the center of mass, because that's where the gravitational force is applied. From the pivot to the center of mass is R if the force is mg. Now in this case, we take the sine of the angle between this. So it's kind of hard to draw. I'm just going to do the best I can. Right, notice that is R center of mass. Okay, the distance from the pivot to the center of mass. So now, one last bit. What direction is this torque? R goes to F, in this case mg. Torque is into the page. So out of all that junk, what do we get? We get R center of mass. We get mg for the force. And then we're going to get a sine of theta here. And then let's think about it. It's into the page, negative k hat. All that is equal to I alpha k hat. And recall here, what is I? Again, that's moment of inertia of the pendulum. And I'm going to state using pivot shown. To be clear, I don't want to get the moment of inertia of a rod about its center because the pivot is not in the center. I want to get the moment inertia of the rod using this pivot. And that's a challenging thing. You'll have to see that in the homework. But I just want to be clear. Don't blindly plug in the center of mass moment of inertia for your pendulum. You have to figure out the moment of inertia using the pivot shown in the problem. Okay, let's clean some stuff up here. A k hat drops, and notice we get a minus sign. That's what I was trying to emphasize here. We usually want a minus sign here. I'll explain why in just a second. I get negative R center of mass mg sine theta equals I alpha. Now, under certain circumstances, theta, well, let me just go to the white. Okay, so let's pause here. this is a derivation. Technically, this has theta in it. This has theta in it. You could call that theta double dot. Remember, alpha is the second derivative with respect to time of theta. All right, is that okay? That's still on the board. Let me get rid of this glare. So we could see this is a differential equation which models pendulums, and we haven't made any assumptions yet. This is valid all the time. So if you were good with making computer simulations, you could use this for large angle oscillations. What I'd like to do now is restrict ourselves to small angles, and I want to show you using another whiteboard what's up with that. We'll come back to this. And I had a ruler somewhere. Okay. Here I have a triangle that's using a 10-degree angle. And I'll just show you, I don't know if you can see this on the board very well. It's about 10 degrees, right? 0, 10, 20. So hopefully you can see that on there. If not, just trust me, it's about 10 degrees. And I just want to point out the length of this side. I guess I used 24 inches or about 60 centimeters, 61 centimeters, something like that. But now notice what happens to the hypotenuse. It's almost exactly the same. So if I use centimeters here, it looks like this is about 61 centimeters tall. And notice the hypotenuse is probably about 62 centimeters, maybe something like that. So we're seeing 1 part in 60, or about less than 2% difference between the adjacent and the hypotenuse when this angle is 10 degrees. All right. So now, and notice here I'm using angles to the vertical. So this is opposite and this is adjacent, as opposed to triangle that's right on the x-axis. You have cosine. Here, cosine is going to be getting this vertical side. Now, I did the math in my calculator. If you care, you can punch this in and verify it. But notice if theta is equal to 10 degrees, that computes to this many radians, about 0.17. If you take sine of 10 degrees, you get about 0.17. If you take tangent of 10 degrees, you get about 0.17. So in short, these are all different by less than 1.5%. Okay. And if we go to 8 degrees, the difference between these two is less than 1%. So in this case, we see the following is true. The small angle approximation if theta is less than about 10 degrees, depending how precise, somebody else, some other teacher might say 8 degrees, but for me, 10 degrees seems to be pretty reasonable for a lot of engineering applications, right? Somewhere in this 8 or 10 degree range. If theta is less than 10 degrees or 8 degrees, we say that sine theta equals tangent theta equals theta. And I guess strictly speaking, I should use approximately equal. All right. So this is what we mean when we say the small angle approximation. Angles are less than 10 degrees. And if you care, I'll throw in one more. Cosine theta is 1 minus theta squared over 2 factorial plus the. If you do the Taylor series and basically keep the first term for sine theta, you get the theta. If you do a Taylor series and keep the first term on tangent, you get a theta. If you do the Taylor series on cosine theta about 0, you're going to get 1 minus theta squared over 2 factorial, which is just 2. All right. So these are the small angle approximations you can use. Notice if theta is really small, this is negligible. Cosine theta is about 1. Okay, let's go back to our board and use this. Come on. Okay. Make sure it's focused there. This is what I wanted to point out. If theta is less than 10 degrees, we can simplify this. And then I would like to erase this right here. just so I have room to work. I'll write it here. Okay. Don't forget to get the direction if you ever do that. Okay, so let's go back to here. We get minus R M mg. We're going to get a theta. And then I'm going to get now. In this case, maybe this reminds you of another equation we got. We had another problem, minus kx was equal to mass times acceleration, which acceleration was x double dot. This was for a mass on a spring. And from this, we found omega naught was the square root of k over m. So this was for horizontal mass spring. I hope you see a pattern here. We see theta double dot equals theta times some junk. The junk relates to omega naught. So let's do that. Let me erase the horizontal mass spring. And let's bring this up. Notice theta double dot is equal to theta times this crazy looking thing. Negative R center of mass mg all over the moment of inertia. Well, that tells me, marker, omega naught for a pendulum is the square root of this garbage, right? The square root of the garbage without the minus sign gives you omega naught. I'm about to fall down. My shoes are sliding wider. Can I get this done? Oh, just barely. Okay. Is that still on the screen? Yes. So this gives you the angular frequency for small oscillations. I want to go more in depth on this in a minute on the next board, but I'll just pause. You could hopefully take a look at that, pause the screen if you need to. So I'm going to next write the equation for theta as a function of time and talk about its derivatives. So let's do that. And then finally, I'll end with an energy analysis if you want. So let me keep going. Let's go to board 2. Okay, so I'm just going to write this up here. We found the following differential equation. R center mass mg all over I theta double dot. Out of that, we made the assumption omega naught must be R center mass mg all over the moment of inertia about the pivot. So what would theta as a function of time look like? Let me see which marker. Will this one work? I think this is a good, oh yeah. Theta as a function of time, one way we could write this is theta max times sine of omega naught t, and then did I want to do plus v? We're going to go, oh, we're doing cosine function. I apologize. So that is one equation that would be valid. The sine equation would also be valid. It would just change what the value of phi is. Remember what this means. If time goes to 0, phi, the phase angle, simply tells you where you start in the oscillation. If phi equals 0, cosine of 0, you start at theta max. If phi equals 180 degrees or pi radians, cosine of t equals 0 would equal -1, and you would start at the left side. So phi just helps you. Do you start at the maximum, the minimum, at the bottom? Where do you start in the oscillation? That's what this phase angle is. Greek letter phi. Remember, this omega naught we've described here is the angular frequency. Think, what is theta max? That's the amplitude. This is the amplitude, the angular amplitude of oscillations. So is this pendulum? Oh, you're not going to do that. Right? That's the maximum angle you swing up to or down, right? Omega naught has to do with this rate of oscillation. I suppose I should probably stick this in just so you need it, just in case you need it. I assume this makes sense. You could get the period of oscillations from this angular frequency, right? So, and maybe you know that would relate to the linear frequency. This is in units of hertz. This is in units of radians per second. That's so sloppy. Radians per second. So, right, and this is in seconds. So just kind of getting you up to speed. Now, I know you're probably tired with this video. Stay alert right here. This is kind of a sneaky spot. Okay, what happens when I take the derivative? Well, the derivative of theta, we're sometimes just going to call that theta dot. We usually call that omega. Pay attention now. Omega naught is the angular frequency. Omega is the radians per second at any one spot in the oscillation. Right? So you're changing angles as this rotates, but the rate at which you change angles is different. Down at the bottom of the swing, the angle changes rapidly. Omega is a large number. Near the top, omega is close to zero because the angle is close to constant. So omega naught has to do with the period of oscillations. Omega has to do with the angular speed of the pendulum. Sneaky. I hope that made sense. All right, so then here, when I take this derivative, I'll get a minus omega naught theta max sine of omega naught t plus v. I'm going to make sure I didn't screw up. When I take the derivative of cosine, I get negative sine. When I take the derivative of what's inside, there's nothing here that's respect to time, but I do get an omega naught popping out. So I get a minus omega naught sine. I still have the theta max sitting around there. And so we see, whoops. There. So notice this term right here. I should be careful. Let me just rewrite this. Notice this term right here, without the minus sign, we could call that omega max. And so notice there's three different omegas in here if you want. There's the angular velocity amplitude, the angular velocity, and the basically, I'm going to call this one the period because it relates to the period. It's not the period. So you've got something that relates to the period, and then we've got the function of time, and then we've got the amplitude. Whoa, three different omegas. Keep that straight. I hope you agree we could take another derivative of this, right? You could get the angular acceleration as a function of time. Repeating this, taking the derivative, you'll get this back to cosine, no additional minus sign, another omega pops out. You'll get minus omega naught squared theta max cosine omega naught t plus v. All right. And so I think that's enough on that. I'm going to go one step further here. I know this is a long video because the screen just turned off. But I want to talk briefly about energy methods. This, you probably don't need this, but you might be curious. Could I do this with energy methods? And let me see if I can do that for you. Come on. Oh, come on. Sorry. Almost there. Good enough. Okay. So now I want you to think about, this works for a simple pendulum or a physical pendulum. I actually did the derivation for a physical and all right. So you can imagine this is a simple pendulum of length L, or you could imagine it has a physical pendulum with radius to center of mass RCM. And I think that's what I did over here. So now in this case, here is a pendulum with a small angle, and you can think about it oscillating up and down, up and down. This small distance here, H plus L cosine theta, must add up to the total length L, which gives us this height. Now, again, if we had a physical pendulum, we're going to use R center of mass instead of the length. And now notice here, I'm saying NGH, and I guess I should be clear. Well, where's my black marker? Here I'm talking about the height of the center of mass plus the rotational kinetic energy. Here again, I is the moment of inertia about the pivot. This is the angular velocity of the pendulum, okay? This is not the one that relates to the period. This is the angular velocity that's some function of time, right? It's speeding up and slowing down as it swings. We see that this must hold, right? That's using this height, plus this, the energy is the total energy. Now notice, to be clear here, I'm assuming this is some arbitrary angle theta, and here I'm assuming it's the maximum. The total energy is given by the maximum, right? When this pendulum is all the way up at the top, it's all potential, no kinetic. So at the maximum angle, you would get NGR 1 minus cosine theta max. Here, this is just theta. This is at some arbitrary angle in the swing. This is the speed at that same arbitrary angle in the swing. For small angles, we saw cosine theta is 1 minus this. Notice 1 minus cosine theta is just theta squared over 2. You get to this weird looking result. Now, in this case, if we plugged in that omega was equal to minus omega naught theta max times, what was it? It was sine of omega naught t plus phi. And if we assume that theta is equal to theta max cosine of omega naught t plus phi, you will see if you plug these in, essentially you're going to get something that will only make sense if and I want to make sure I get the right omega naught. If you plug these in, you'll have some equation that will only make sense if omega naught is this result. So that's a different way to derive this period of small oscillations. And I pointed at this and said period. Remember, this is an angular frequency of small oscillations, which relates to the period of small oscillations. So if you need extra help with that, you can talk to me in office hours, but just plug it in and then you'll see that if you plug in this omega naught where right here, it will get squared, everything will work out. You'll get sine squared plus cosine sine squared plus cosine squared equals 1 to make this match up. All right, let's go ahead and stop the video there. Oh my goodness.